Let's take a look and stand up if you want in order to truly appreciate our last topic in season 11, and that is standing waves. So I'll explain what a standing wave is, but if you want to stand as you watch this video, just to kind of get in the spirit, that might be the way you want to go. I'm not saying you have to, but here is this is actually going to introduce a really, really cool way to look at standing waves. This is a table covered with salt. It's just regular table salt, and the table will vibrate at different frequencies, right? So remember frequency, or quiz yourself, what is frequency? If you said frequency was vibrations per second, or cycles per second, or up and downs per second, that's right. So this table can vibrate at very high frequencies, and I'm going to turn the sound on here and let you see what standing waves look like in 3 dimensions like this, because we're not going to work on them in this interesting way. We're going to work on them in a less interesting way on strings and in air, but this is kind of a cool introduction. So the frequencies here are going to get pretty high, so I'd recommend, I'm going to turn the volume down now. I don't want to blow your eardrums out. I know if sometimes the videos are a little loud. All right, so the definition of a standing wave is below. It's a wave pattern that develops when 2 waves of the same frequency, amplitude, and wavelength travel in opposite directions and interfere. So it's easiest to understand on a string. So here is a string, and we've broken the string down into air quote particles, right? So it's easier to see. And we're going to let the wave travel down the string. So we see the wave traveling down the string, and this is a fixed end. It's a fixed end. So what's the reflection going to be? Is it going to be on the same side or opposite sides? Make a prediction, and remember from a previous video, you should know that. Here we go, very exciting. I'm going to do drum roll. And, okay, so I'm going to pause it right here. The reflected wave, you should know, is going to be on the other side, and it's going to start traveling back down the rope this way. But there are more and more waves coming. You might ask, how is it possible to create so many waves? Well, you've done it, or you will do it in lab with a slinky. You just shake it repeatedly at a constant rate back and forth, so the frequency is the same, and you can create your own standing wave. It's amazing. But what's going to happen here is as this reflected wave goes back, you're going to see areas of interference. So let's watch what happens. Okay, here is our reflected wave in blue. Now notice it just passed an incident wave that was traveling to the right as it traveled back to the left, and they created an area of constructive interference. But the reflected wave is soon going to encounter another incident wave, but this incident wave is on the opposite side, so they're going to create an area of destructive interference and cancel out, which we'll see right here. Right? So at this point, the reflected wave is here, the incident wave is here. They create destructive interference. And let's let the video run, and you're going to see this repeating throughout the rope. Here we've got constructive interference. Oh, look, our second incident wave now, a reflected wave. Oh, constructive interference there, destructive interference there. Now, what is really happening to the string is, watch what happens to the string. A pattern begins to emerge. And there are points on the string, here, 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 and here, where the slinky or the string itself doesn't move. Those points are called nodes. Those are places where destructive interference occurs and the string doesn't move. Then there are places here where there's maximum amplitude. Those are called antinodes. Okay, so these are two key words to remember. So there's a node and there is an antinode. All right, so let's take a look at standing waves on a string and see if we can learn a little bit more about that app we just saw.
Well, let's go a little higher. So it's sending waves back and forth, but these waves are out of sync, if you like. They're not exhibiting consistently constructive or destructive interference at any one point. But if I set it here, for example, I have what's called a standing wave. That is, the wave that's sent down and reflects constructively interferes with the next wave that comes down right at this point. Now the waves that come down and reflect destructively interfere with the incoming waves right here. And that's called a node. I can touch it and it still is working. So the node is not moving. Here it's moving up and down, and here it's moving up and down. And we'll see that in a second with the high-speed camera. So here we have what's called the second harmonic. It's the second possibility for a standing wave for a string that's held at both ends. Because notice, this is a node, and the middle's a node. So we have three nodes for this wave. Now, like I said, second harmonic, well, what's the first one? The first one will be half this number, so 8.5. And there we go. It's basically the scenario of a jump. Now, I can find all of the other harmonics are multiples of this number. So we just saw that 2 times this number was the second harmonic, or the second possibility. Well, if I go 3 times this number, I should get the third harmonic. Well, 3 times 8.5, I guess that was that around 25.5. And there we go. So that's the third harmonic. How many wavelengths is this? Well, it's 1 1/2. 1 1/2 wavelengths. And it's easier to see in high.
So looking at the third harmonic, it's pretty easy to see there's 1 1/2 waves. From here to here is a complete wave. This is half of a wave and another half. So this is one wave, and then this is another 1/2. So maybe you could see a pattern. First harmonic is a half wave. Second harmonic is one wave. Third harmonic is 1.5 waves. I'll give you a quick quiz question. He's going to go up to the 6th harmonic. How many waves will be in the 6th harmonic? Well, let's find out.
The 6th harmonic. The 6th harmonic will just be double this frequency. So we go up to 50. And there we go. That's the 6th harmonic. Beautiful. And it's 6 times the fundamental frequency, which we measured in the beginning to be 8.5 hertz. So check this guy out. We have 1, 2, 3 wavelengths. And in the next video, the explanation video, we'll go through the calculations and the derivations.
This is by far my favorite way to look at standing waves. What you're going to see is a Rubens tube, which is a metal pipe basically filled with methane with holes poked in the top so the gas can come out. And when you send waves through the tube at certain frequencies, you get the fundamental, you get the 2nd harmonic, the 3rd harmonic, and so forth. And you're going to see this in a beautiful way. We'll do this in class, but enjoy your introduction to a Rubens tube.